Yes, I'm ready. All right. So my name is Bickhart. I'm going to talk to you today about some research that I did. This was my master's thesis at the University of Delaware. So I graduated 2 years ago, and I've been working on the code initially, and then just recently I've been porting it to FreeBSD 7. So I'm going to talk about this today. So what is this? I'm going to talk to you about the transparent TCP-to-SCTP translation Shim layer, which is quite a mouthful. So basically, a lot of you may not even know what SCTP is. I know I've talked to some people and they do. So I was kind of torn between how much SCTP detail and then how much of the project detail. So the compromise I came up with was to give a brief overview of SCTP and just what it is for those who may not know, and just give pointers if you want to look into it more yourself. So basically, what we're showing here now is your typical 5-layer internet model. So you have your application transport network, data link layer, and physical layer. And so SCTP is a transport protocol. So it's equivalent to TCP or UDP at that layer. And it's general purpose, so it's like TCP or UDP. You can use it for whatever you want to do. So a little bit about SCTP. It's connection oriented, it's reliable, and also partially reliable. There's an extension which I'll talk about in a minute. It has TCP-friendly congestion control, so congestion control is similar to what TCP does. So it's message-based, so in that respect it's more like UDP. You send one message, the whole message is received in full by the other side. It's not stream-based. So one of the things I added today is there is a partial reliability extension to SCTP. So you can actually have your data be partially reliable. You'll send it with like a certain time where it'll be considered valid. So if you need to retransmit it within that window, you'll retransmit. If it gets too stale, then you just throw it away and forget it. So that might be good for applications like streaming audio or video, where once you get past a certain time frame, the data is not worth it to continue trying to send anymore. And so the two, probably the neatest things about SCTP versus TCP are its multistreaming ability and multihoming support, which is what I'm going to focus on today. And so for the details, you can see the RFC. And if you just Google SCTP, you'll find a lot of stuff that's going on right now. So the idea of the project, we're translating TCP calls into the kernel to SCTP. Simple enough. And so the transparent part of this is that applications won't know this is happening. So the application is a TCP application. It's written in normal style that you would write a TCP app. And so the kernel is actually doing a little switch under the covers and using SCTP instead of TCP without the application have any idea that this is happening. And so the Shim layer just describes how we kind of slide this logic into the sockets layer of the kernel. And most everything above and everything below is the same. You just do a little fiddling around in the Shim in between to control this. So the outline of the talk today, I'm going to talk the motivations why you'd actually want to do this in the first place. Then go over the implementation a little bit. I'm not going to touch on every single system call because a lot of them aren't that interesting, but I'll talk about the more interesting aspects of it. And if you have, there are some issues and things you might think of, like, oh, how does this going to work? And so feel free to ask. A lot of it's not in the slides, but if you do have questions about it, just feel free to interrupt at any time and ask questions. So then after that, I'll talk about a little bit about how you control it on your system if you do have this Shim layer built into your kernel, how you go about using it. Then some experimental results with the implementation that we had finished earlier. So the original work was in FreeBSD 4.10, and I've been porting that to FreeBSD 7 now, so adding all the locking and SMP related stuff. So that the demo today is actually going to be in the 7 code. I've got it mostly working now. And then some challenges in future work. There are some issues, certain applications have problems, and there may be ways to fix that, so I'll talk about that there. And then I'm going to do a demo and actually show you the shim working. So going back to like the main reason or motivation for why you would want to use the shim is multihoming. So in TCP, you have your 4-tuple, your 2 port numbers, your 2 addresses. So just for example, say you have 2 hosts A and B, and you have 2 interfaces on each one, A1 and A2 on host A, and then B1 and B2 on host B. So TCP, if you're going to have a connection between these 2 hosts, you'll have one of the 4 combinations. You'll have A1, B1, or you'll have A2 or A1, B2, A2, B2, or A2, B1. You get one of the 4, and that's all you can get with one TCP connection. So SCTP has multihoming built into the core design of the protocol. So you have, instead of a connection, you have an SCTP association that incorporates all of the addresses on each host. So basically you have, this is theoretical because of routing and different issues like that. Not all of these may end up being valid paths through the network, whatever network that might be. But in theory, you could have potentially up to using all 4 of these different paths with SCTP. So why would you want to do this? Basically, you have fault tolerance. If you have your association up, so you have all 4 of these endpoints in it, so say for example, and your primary destination is where you're actively sending data. So say you're sending data from A1 to B1, that's your primary path, and you're sending data, and you have a failure. So the destination address B1 is no longer reachable from host A anymore. So that path and then the other path that also uses B1 as its destination is no longer usable. So what SCTP can do that TCP cannot do is it can fail over and then start using B2, which is an alternate destination, and transmit data there instead. So this is not a new connection getting started. This is the same association just fails over to the other path, and your data continues uninterrupted. So another bit of research that some of my colleagues were doing at the lab before I graduated was the idea of doing concurrent multipath transfer. So if you do have 2 paths through your network that are independent and they don't share bottlenecks or other issues like that, which is a research topic they're still working on. Let's say you do have 2 paths through your network. It doesn't really make sense to only transmit data on one if you have bandwidth that's idle on the other path. So the idea with CMT is to actually send new data to both destinations concurrently, with the hopes that if the paths are independent enough, you can actually, say, in theory, double your bandwidth if both of these paths have the same bandwidth. It's not exactly double because of other issues, but you could potentially increase it by a pretty large factor. So that takes care of the problem of if you have other valid destinations, they're not sitting idle, wasted, just waiting for a failover. You can actually use them in non-failure conditions. So Janal was working on this. He's graduated, and this is actually his dissertation, this topic. So there's going to be links at the end of the presentation if you want to follow up and look at more information about that. So those are the 2 main motivations of why you would want to actually do this translation from TCP to SCTP. Multihoming, and then in the event that the CMT becomes very mature and usable, you can get both of these things for free, basically. The only problem is, how do you actually use SCTP instead of TCP? You don't want to rewrite all of your thousands of TCP applications, because that would be a lot of work. But then the other problem is, say you do write an application that uses SCTP natively, so you do make the effort to port it and use SCTP. You have the problem, why waste your time if no one else is going to use it? You could write your web server to use SCTP instead of TCP, or both. But if no browser is actually going to follow through and do the same thing, what's the point? So that's what the Shim attempts to solve. So it's both translating from TCP to SCTP on both endpoints, but also translating from TCP to SCTP and then talking to a native SCTP endpoint on the other side. So I'll show, there's going to be diagrams about that later. So just an overview of implementation. So I mean, typically the way you have your TCP application and you have the transport layer. And so you'll invoke system calls that will go down to TCP, and TCP will connect, send data, and receive data and other things like that. So the idea of the shim is to slide this logic into the kernel and then intercept your calls for TCP and instead reroute them to SCTP. So that's the general essence of what the shim is going to do. So the important thing I'll just go over again is that applications are not changed whatsoever. You go in and CD to the port and then make install clean and then run it, and with the shim you can use SCTP without having to touch your application or rewrite it. So like I said before, the initial work was in the 4.10 kernel, and then working on getting it all squared away for the 7 kernel. So sometimes people ask, why would you do this in the kernel as opposed to a library? And so I actually know of one project, I forget the name or who was working on it. It was back in the early days when SCTP was just getting more well-known. And it was basically a loader hack that would load a hacked up version of the stub functions like connect and everything that you would call. And in those cases, your application would turn into SCTP, but that's it. The reason that we ended up doing kernel implementation is we actually have a hybrid approach. So you'll try to connect with SCTP, and in the event that the other system, that particular server is not actually using the shim or doesn't have SCTP sockets available natively, or it's just not there, it'll actually fall back to TCP and then use that if it can. And there's some other reasons. Basically, you just have, in the kernel, you have a lot more access to things you can fiddle around with and manipulate.
Why 4.10?
That was what was stable at the time.
When did you start working on this?
It was 2 years ago that I did the work.
When in your first slide you said the application can send messages, not stream-oriented. So that means the application has to change. But here you say translation from TCP to SCTP is transparent to applications, so no modifications to applications whatsoever. That means that is not the same. First you said the application can do messages like UDP, and here you say no modifications to applications.
Oh, okay. So since TCP is stream-based, if you actually send messages that's SCTP, that doesn't matter. It's only the opposite that's a problem. If you have UDP, you can't map that to a stream-based protocol necessarily. So for at least going from TCP to SCTP, it doesn't matter because TCP can arbitrarily segment the messages as it pleases. So since SCTP is message-based, where it chooses to send messages is basically just the same as what TCP does. And so basically, from an implementation point of view, what you have to consider that's not in the typical 5-layer model is the socket layer in the kernel where all of this magic happens. So this is just, everyone in here should probably know this. It's probably written this exact code before, but you create a socket and you get a socket descriptor back. And that's what all the application sees. That's the endpoint for how you communicate with your peers through the socket descriptor. And so within the kernel, you actually have your descriptor table of all your files, including your sockets. And you actually, then you have socket objects that the descriptor maps to. And the sockets are within the kernel that the application can't mess around with the contents of those except through the normal APIs. So you can connect to your socket, send and receive data, and close it, and everything in between. So the format of a socket, kind of conceptually, this isn't the exact data structure by any means, but you have a pointer to your protocol which has the function pointers and hooks for all of those protocol-specific implementations. Then you have your state, your configuration, send and receive buffers, and so on. And so when you actually create a socket, if you do fill out the protocol field, that refers to which protocol block gets associated with your particular socket. So what the shim does is it adds a couple fields to the normal socket data structure on the system. And I'll get into more of what these are and what they're used for in the following slides. So the way things typically work, you have your regular TCP socket. So your application will create a TCP socket. And then at the same time, this hidden SCTP socket will get created. So the TCP socket basically points to this hidden SCTP socket. So you have both of these available in the kernel for your any TCP socket that's created will have this hidden shim one available. And so there's also a parent pointer back from the hidden SCTP socket to the parent and some state. So if we kind of explode into the socket layer, we can see that there's the system call stubs, or the functions that your application calls, like connect and other things like that, which package up the parameters and then make the system call into the kernel. And in the kernel, you have your system call implementations. And then in turn, those call other lower level functions on sockets, which in turn call into the actual implementations of your transport protocol, whether it's TCP, SCTP, or UDP. So basically same format over here. So the interesting thing about these different layers from going from the application to the transport and the socket layer in between, the two at the top operate on socket descriptors. So they're basically integers that are your socket descriptors that go through your file descriptor table and then lead to an actual socket. And the lower level functions, the socket layer functions and the transport protocol implementations actually work on the socket objects themselves. So what we're going to look at in the middle is the mapping from where a socket descriptor gets changed into either the normal TCP socket or the hidden socket. So a lot of how the shim works is carefully deciding at this level here which socket you're going to pass to lower layers. So that I'll explain here. So typically the way your system calls for the network protocols work, you have the generic requests coming in on a certain socket. So say you want to connect, send, receive, and so on. And as I mentioned too in the first slide, each socket has a pointer to all the hooks and interfaces for that protocol. So if you get a generic connect request, you'll look up in your table for this protocol, okay, what function actually implements connect? And you'll say, okay, it's a TCP socket, so we'll call TCP's connect function, or TCP's send, or TCP's receive function. It's pretty much the same thing for SCTP. You have a socket that has the protocol associated is SCTP. So if you get a connect request for that socket, it'll get mapped to the SCTP connect implementation. So the way we can control whether TCP or SCTP is used is by passing either the normal TCP socket or the hidden shim socket. When you make that choice, you can control what happens. If you pass the TCP socket to the lower layers, say connect, that TCP connect happens. If you pass the SCTP socket to the lower layers, an SCTP connection happens. So now I'll go over how a client using the shim connects. So like I mentioned before, we take a hybrid approach where you fall back to TCP if SCTP is not running on the other side or that particular application is not enabled for it. So your application will call connect, and then it'll first try to do SCTP. So this supposes that you have it configured to actually try to use the shim for this particular application, and I'll talk a little bit about how we control that later. So in the event that SCTP is on the other side and listening and everything gets set up fine, then you return and your application has an SCTP association rather than a TCP connection set up, and can use that for all of its usual I/O over the network, just through that same mechanism of swapping which socket you actually send to the lower layers. Now, what happens if SCTP is not available on the other side? Then you'll basically detect this error, and then the shim will fall back to just starting a TCP connection as usual. So when you're using the shim, you never really have to worry, what if the other side doesn't support SCTP? It's taken care of for you. Basically, the cost is one round trip time to find out that SCTP is not there. So on this
question,
sure.
Is the application aware of which path has been chosen?
No, so that's one of the interesting questions about SCTP. So one thing that you're stuck with is what the application does, which may not always be the smartest thing if you know you're using SCTP. So I'll actually talk about this after this slide because it kind of pertains in some ways more to the server listening than for the client connecting. So I'll get back to that. But so basically for your server, you create a socket, you bind to some address and some port number, and then you listen on the socket and then service any clients that connect to that listening socket. So no surprises there. What we do in the case of the shim, if you have the shim enabled for this server, your application will call bind for the address and port number that it wants. Then the shim will actually duplicate the bind calls to TCP and SCTP. So you'll be listening to both port X for SCTP and then port X for TCP at the same time. So you can actually then listen. It's handled the same way. So your application will then be listening on the same port for TCP and SCTP concurrently. So you'll be able to handle clients of either type connecting. So a little bit more detail about how the server actually works. Okay, so to answer your question, with TCP, like say you have a server and you provide some IP address that you're going to bind to. If you do, so with TCP you would just bind to that address and that address only. With SCTP, you may have other addresses available on your system which you could bind to. And because your application is written without knowing that this is possible, you can limit yourself artificially to that one address that's specified. So one of the things I added to the kernel is a syscontrol that lets you force, if you have a client, if you have a server listening, it can force it to bind to all the addresses, not just a single address. So it's kind of a way to get around that limitation. If you enable that syscontrol, then when you do, even if the application specifies one address, you'll actually bind to all of them if you end up using SCTP.
Question 2. If you enable the shim, is it available for all applications at the same time, which means all applications use the shim, or can you turn it off or on by environment variable?
So I'm going to talk about that in a few slides, but the short answer is you have some control over what applications use it and which ones don't. Okay, so for the server side, you have your application, you have, just for the TCP case, if you think about that first, you have your listening socket, and then you have the protocols at the transport layer. So the application will call bind first, and then listen. So the application is ready to service clients. So suppose you have a TCP connection come in from the network, you get a SYN, and SYN ACK, and then ACK, and so your connection is then set up. So what normally happens is your new socket for the connecting client is created, and then put in a queue off of the listening socket. So your TCP clients can fill up here. And then they're returned to the application by calling accept, basically. So all the clients that have their connection is established and they're waiting for I/O are returned to the application with accept. So once a socket's returned to the application, it's pulled out of this queue of waiting connections. So from before, I talked about the hidden socket. So in the server case, the hidden SCTP socket is also linked off of the parent TCP socket, and it's also bound and listening to the same port number as the TCP socket is. So now, suppose you have SCTP association coming from the network. You have, in SCTP, it's actually in a NIT packet instead of a SYN, and you go through the handshaking process and create your SCTP association. What would normally happen is you would have your waiting SCTP socket chained off of the listening socket there. So when I was actually doing the implementation the first time, I was going to do it this way and actually have two separate queues. And then I was thinking about in accept, how do you pick which queue to service and what order and which one gets priority. So rather than deal with all of those problems, I ended up deciding to use the Shim's parent pointer. So the hidden socket points back to its TCP parent socket. So using that pointer, instead of putting the socket here, we can actually just put it into the queue with the TCP client sockets. And the neat thing about this approach is, since each socket points to its protocol, you can have these sockets basically mixed in together. And when the application gets it back through accept, and it calls whatever I/O functions it wants to do on the socket, the actual behavior of what transport protocol is used is decided by what type of the socket is. So you can have the sockets all mixed together in one queue, and then the application doesn't really need to know that it's one type or the other, since the socket itself contains the information you need to decide which protocol to use. So to answer your question about controlling the Shim, so the first step was just a global on-off switch. Either Shim is on or Shim is off. And that's not really very precise, because you may know certain applications, it's not going to work very well, or in some cases, which I'll talk about later, it doesn't work at all right now. And in some cases, you know maybe for sure the other side is using the Shim and you just want to try it specifically for that application. So you want your administrators or the system to have finer control over which they're actually going to use. So the solution that I came up with was to basically allow you to enable or disable the Shim using rules that would match certain application use of the network. So you can match on the addresses that you are either listening to or connecting to, what subnets you're trying to connect to, and either a single port number or a range of ports. So there's basically two cases for the global on-off switch. You have a default for your listening sockets, and you have a default for basically remote peers that you're going to connect to. So there's an on-off for both of those. So I called those like local and then remote. Local listening sockets, remote sockets you're going to connect to. So you have chains of rules for each of those. And then for each of those, you can have a policy, which is either enable or disable. So this rule struct is basically, you have the chain, the policy, and then the matching criteria, which are the addresses, the subnet, and then your port number or range. So if you do match on one of these, you use that policy. Pretty simple. So just example of the rules. For this one, it's for local listening sockets. The policy is enabled, so the address and subnet are wildcards. So basically, if you're listening on port 80, then you enable a Shim for that. Likewise, for this one, it's remote, and if you have a subnet here and everything else is a wildcard, so if you're connecting to a server on the subnet, then you enable a Shim. And then an example of disable, if you're connecting to this specific IP address and a port in this range, then you want to specifically disable the Shim for that application. So this all comes to play with, and also is affected by the global setting for each one. So suppose that you have your global setting it's off for connecting to remote sides and also off for local listeners. So by default, you don't use the Shim for anything. And then so you divide up your rules into the 4 chains. So for local and remote, and enable, disable, you have 4 combinations. So the rules fall into one of those 4 categories. So you have chains of rules for each of those. So say, for example, your application calls connect for this IP address and that port number. So what you would do, first you would check your global policy. So your global remote connection policy is disable. So by default, you're not going to use the shim for this connection. So you want to look for exceptions to this rule. So you would look in the remote enable chain. So you would say, OK, let me check here and see if there's some rule that will specifically enable, even though the default for this will be disable. So you'll basically go through the chains of rules attached here and then find the first matching one along the way. So the way it's written right now, the first match will be the one you use. So you need to be careful to order them correctly. So if you have the most specific ones should be first and then general ones later. I mean, at some point in the future, you could easily add some kind of sequence number to order these and then change the order. But for the moment, I haven't done that. So with this control mechanism, you can control your needs to fit either individual administrator preferences or sites, and then what applications you either have specific knowledge will work correctly or that won't work correctly and you want to avoid. And so you can change how aggressive you want to use it, either enable it by default and then hope for the best, or leave it disabled and then enable one applications you know will work okay. So it gives a lot more fine-tuning ability than just an on-off switch. So any questions so far?
I've seen only 4 addresses in your examples. Do you support that music?
That's one of the things I'm working on. It's mostly there.
You talked about a server application to bind to multiple IP addresses.
Right.
What about a client application? Is there a similar?
So the syscontrol applies to both. The way SCTP usually works, if you connect, it'll just send. So your SCTP has an init chunk, and then init ACK, cookie echo, cookie ACK. That's the handshake. It's basically the parallel of SYN and SYN ACK. In your init chunk, by default, SCTP sends all of its addresses. So if you do connect with the shim, the first init will have each address from your system. And then the other side will send its addresses, and then there's a heart beating mechanism where each side will try to determine which one's reachable. And then basically.
So if I have a multi-home client, the shim layer automatically uses all available.
It'll advertise all the addresses. Which ones actually can be used depends on the heart beating and reachability. Yeah.
Do you know if any firewalls support SCTP?
If any.
Firewalls?
So that's one of the issues right now with SCTP. I think a lot of your average home router that does NAT doesn't always handle SCTP correctly. So I'm not sure of the details on that off the top of my head, but that is a problem area. Just even in general, not even just for multi-homing, but just trying to use it between two home routers on the internet could be problematic.
My question is related to the last question. Have there been changes made to applications like netstat or TCP dump? Do they?
TCP dump does do SCTP. Netstat I don't think does, because I was looking at it the other day and I didn't. Oh, he did? Okay. Yeah, the code I'm using is a couple months out of date, so I don't have the latest and greatest. So it may be in there now. But like Wireshark and other things, which when I do the demo, you'll see today, do handle SCTP.
So you say you're working on this for 7. Have you dealt with the locking issues between the two sets of PCBs you're going to have talking to each other in the kernel?
There's still some issues left, I think. I had a few.
You didn't say what locking issues.
I had a few deadlocks this past week as I was trying to get everything working. Like new cases that hadn't been tested yet that I was getting ready to test before the demo. And so there are...
Bugs in FreeBSD?
No.
Certainly not the notes.
And not locking bugs.
Do you have any issues with applications that try to use somewhat more obscure TCP socket options and things like that?
So the socket options are, at least for the main ones you have to worry about, well, at least for sure the TCP socket options, like TCP no delay. The handy thing about that is SCTP has the same options to disable NAGL. So for the options that apply to TCP that SCTP also has corresponding options, it's like a simple translation. If your shim is enabled, check if it's one of these options. If so, change TCP no delay to SCTP no delay before calling the rest of the way down. So more obscure socket options, that's one of the issues right now. I've tested a fair number of applications, which I'll talk about this more later. But I mean, obviously, I haven't tested everything. So, since the way you write a network application, everyone writes it a different way and uses different calls. So sometimes there can be quirky things where an application doesn't work correctly, and some of that is figuring out those corner cases that are legitimate and making sure the shim can handle them. And I found a lot of things like that, and some of them have been handled, some of them are still work in progress. But I'll talk about the specifics later. There's two cases that we'll talk about.
Sorry? Wouldn't it be less overhead if you could also control the shim just by the application name, not by some range of 5 devices? Or is it only done at when you open the socket?
So the way it works right now, the control is actually when you either call bind or you call connect. So it's looking at the addresses. I guess it would be possible, maybe, to actually use the application name.
Like libmap or something. Like libmap does. Similar way.
Yeah, I mean, it's probably something it's doable. If right now, I don't do it that way, but probably something possible. So kind of going off with the other question, applications I have tested so far. I've tested Telnet, SSH, HTTP with Apache and Firefox, and then streaming audio with Icecast and XMMS. Those do work correctly over the shim. So if you enable the shim for both sides, you can use all of these. And from your application point of view, they look the same. If you weren't sniffing the network or watching the packets, you wouldn't know the difference.
What about FTP, and would it run faster?
FTP, I have a...
With HTTP, when you download a file?
So I actually do have results about that some of my colleagues from the lab did. And FTP is actually an interesting case. If we have enough time, I'll go over it. I might skip it depending, because it's somewhat in-depth. But FTP is one of those applications where, because of the way TCP works with the half-close, SCTP doesn't have a half-closed state, so you can get weird, quirky behavior. But if we have time, I'll talk about that specifically. So what I talked about before, there's basically two ways you can use the shim. One is you have a client and server that are both TCP. So you translate from TCP, this orange part here represents the translation that the shim does. So you translate to SCTP, have SCTP through your network, and then it's translated back to TCP for the other side. So in these cases, I tested with Telnet, SSH, and HTTP, and the streaming audio also. So that works fine. Then the other case is that if, say, you have a server that's written natively to support SCTP. So there's actually a version of Apache that the application actually listens on TCP and SCTP. So if you have, say, Firefox and you turn the shim on, you can connect Firefox unmodified normal TCP, thinks it's talking to TCP, to translate that to SCTP, and then talk to a native SCTP socket on the other side. And that also works. So those are the two main modes that the shim can provide. So this is the more interesting one. Well, they're both interesting. The first one gives you multihoming support and the fault tolerance that comes with that. This one solves more of the incremental deployment problem, where you have a server where it gives people an incentive to write things in SCTP, because you know using this, a TCP client would be able to talk to your server, or vice versa. Okay.
It would seem that the application at the server would have to know that it was talking to a TCP client, a shim client, right?
No.
Otherwise, it can't use any interesting features.
What interesting? Okay, so yeah, that's one thing. Yeah, if your server, so a multi-streaming is a good example of that. SCTP supports multi-streaming, so you have multiple independent data flows that don't have head-of-line blocking. Your application has to know about those to actually use that. So yeah, that's a good point. Not all of SCTP's bells and whistles can be used for these cases. So we do have, I did some performance measurements just to compare performance. And so basically we have this set up here. I was measuring file transfers with SCP, and then tested with a bunch of uniform loss rates, like 1, 3, 6, and 10%, different file sizes. And so all the data, there's graphs on the next slide, is the average of 30 runs, except for the smallest files, which because they're so short, if you lose one packet at the wrong time, it can widely vary how long they take. So that's an average of 90 runs for that one. So here are the results. So the orange line is TCP, and the green line is the shim running with SCTP. So obviously lower line is shorter file transfer time. So you can see at low loss rates, they perform pretty much equivalently. Like no loss, they're about the same, where TCP might be like a hair ahead, but effectively the same. As the loss rates start to increase, then SCTP outperforms TCP by a pretty wide margin. And that's not really a fact if the shim is better for anything else. It's just SCTP has, the congestion control is a little more advanced than what the average TCP implementation uses. So basically just interpreting the results. For low loss rates and small files, they're equivalent for the most part. At high loss rates, SCTP can be potentially a lot better. Most of that is just SCTP is a little bit more modern. It's designed so it uses SAC for everything, and then other features like appropriate byte counting. So you actually consider not just the number of ACKs, but how much each ACK is ACKing. And so the other important thing to take away from this is that using the shim is not going to be any worse than TCP, and it could be potentially a lot better.
Which TCP implementation was used for the reference? Did it have ABC and?
So it was, I think TCP in FreeBSD 4.10 is New Reno. So I think it has, I don't know if it had SAC or not.
No, I don't think it has.
I don't think so.
ABC,
it definitely doesn't have ABC.
That's why I'm asking.
Yeah. I mean, so the point of this is not to say SCTP is better. It's to say that using these two implementations that were like both contemporary at the time, SCTP is not going to make you any worse off and could be potentially better. If TCP improves and like uses some of these ideas like SAC and ABC, then it could be better too.
I don't know if I'm sorry if I've covered this already, but if you have two FreeBSD applications both running with their shims, and none of the applications are SCTP, will you still get that benefit? Can you actually use the shims to communicate?
Yeah. Yeah, so if you have the shim enabled for the listening side and the connecting side, and say they're both set up and it connects and works, then you'll use SCTP as your transport. So you can actually use it with two TCP apps on either side. So some of the future work, so one of the things, the question earlier about quirky socket options and things like that, and also FTP, there are some cases where applications, because of how they're written and how TCP works, the same thing does not always map exactly onto SCTP, and you can have problems. So one of the problems that we found initially was if you're doing connect on a non-blocking socket, and you are using the shim, but say the other side does not have SCTP. So as you can, I mean, I've showed so far, pretty much all the interaction with the socket layer and with the shim is application driven. So application calls connect and you switch the sockets, or an application calls send to receive and you switch the sockets. The problem is so you say you have a non-blocking connect, like here. So this is the non-blocking case. Your TCP application calls connect, and then so the shim will try to set up an SCTP association. And since it's non-blocking, you just return immediately. The question is, what happens if SCTP is not available on the other side? So you get to this point, and you've already returned, so what do? You're not in the connect call anymore, so you can't go back to TCP. So you're kind of stuck here. So the code that I've added, I've just been working on this in the last couple of weeks, was basically, so what does an application do after it does a non-blocking connect? Maybe it starts some other connections, does some stuff, but eventually it's going to call select and then wait for the file descriptor to be writable, which will show that either the connection is established or it's failed. So what I've done, the kernel actually in the select implementation calls poll for the socket. And what I've done is in poll, the first time you call poll after you tried to do a non-blocking connect with SCTP, you'll check to see if there's an error on the hidden SCTP socket. And if there is, you basically kickstart the TCP connection from poll and start it there. So that will start. And so at the time, you just return nothing. You'll continue blocking and select. And so the TCP connection will get set up. And then that should cause a wake up. So then you'll select, will poll again, and then pull the TCP socket and see that it's connected, and then return. So the other issue, that the main difference between TCP and SCTP is how the closing works. So TCP has the 4-way handshake that allows a half-closed connection. TCP has a 3-way handshake that does not allow a half-closed state. So the main difference is in TCP, if one side closes, the other side can still happily continue sending. But with SCTP, if one side closes, immediately, once the other side receives the close, the connection gets torn down. So you can't have this kind of waiting state where one application has closed but the other hasn't. The first close will actually tear the whole thing down. So that turns out to be a problem with FTP. So probably everyone's basically familiar with how FTP works. The client, if it's going to download a file, issues the port command and then gets the response back. And then it'll send the retrieve to actually start the file transfer. So when the server side receives the retrieve message, it'll open up this data connection. So the dotted lines are the data connection, and the solid is the control connection. So it'll connect to the port that the client specified initially. So say everything, this is for SCTP, so say, oh sorry, TCP. So you get your SYN, the data connection gets set up, and then say, after the data connection is set up, then the server sends the 150 message to the client, and that tells the client, okay, the connection is set up, start reading. So say you lose this message, and if you have enough room, enough buffering, and let's say the file is small, TCP can actually transfer the file before the other side is called accept. So by the time, and it can do a half close here. So by the time the 150 message gets retransmitted, the whole file has actually been transferred and it's just buffered on the client side. So the client calls accept and then reads everything all at once, and then connection gets closed. So works fine for TCP. With SCTP, we run into a problem. So this is the connection setup sequence I was talking about for SCTP. But say here we lose the 150 message. So same as before, the file gets sent, and then the application calls close, which causes the shutdown complete. Since there's no half close state, this actually kills the whole connection. So by the time the 150 message is retransmitted, you call accept and the connection's already gone because it's been closed. So that's one of the problems you can run into with the Shim, is applications that are written with specific knowledge of how TCP works. You can hit this kind of issue here, where because there's no half closed state, this connection is already blown away by the time you get around to trying to accept it because of losing the 150 message. So one suggestion that one of my colleagues had made was, in SCTP you have streams. So if you're using the Shim, you can't use the streams for the application data because the application needs to be aware. But what if we use one of the other data streams to actually send messages about the half close between the two sides? So one possible solution would be when you, so if you're using the shim and one side calls close, basically you, instead of actually doing the close at that time, send a message on one of the other streams and say, okay, the other side closed. That way the other application will actually be the one that really initiates the close when it closes. So whichever one closes first, it kind of ignores the close and just tells the other side that it should be the one that really initiates the close. So I haven't done anything with that yet, but it's a possible solution. So now I'll do a demo real quick. I just need to reboot this one computer. So the demo is going to be using XMMS and then an Icecraft streaming server over 2 different networks. So I have 2 crossover cables here. So each computer has 2 interfaces. One is the 10 network and one is 192.168 network. So what I'll show is that for TCP, if you're streaming audio and listening over the network and you unplug, obviously your music is going to end very abruptly. And TCP, since it doesn't have any awareness of these other destinations in the connection, the game is over and you're done. With SCTP, we have an association that has these 2 different paths that are available. So in the event that you're streaming music and you get interrupted because your cable gets unplugged or a monkey chews on it, like the other presentation, then what SCTP will do is fail over and then start transmitting the streaming audio data to the alternate destination, and your playback will continue uninterrupted. So I'll put the further reading up again afterwards. Just let me get the demo ready. So what I'm going to do, I'm going to open up 2 capture windows, so capture from both of the 2 interfaces on this computer. So IceCast is port 8000. So right now, this computer is the server. So on this side, the shim is enabled for port 8000, and I've started IceCast. So it's listening on the TCP 8000 port and also SCTP 8000 port. So first I'll show what happens with TCP, and then I'll show what happens with SCTP. And if you don't like the music selection, I apologize in advance. There's just a couple random songs that were in OGG format. So this will be TCP, sorry. Is that it? Oh wait, hold on, I can change the volume on here. All right. So right now you can see all the streaming is over this interface, which happens to be the back one here. So if I pull the plug, oh, that wasn't very much fun. So you can see what happens. It's pretty catastrophic with TCP.
Now you finally know why the ape would bite your kid.
So what I'll do now is turn the shim on for XMMS. So I have a little program that controls it. So it's called Shim rules. So right now you can see there's no rules been added, and the defaults so you can see the local enable and remote enable are both 0. So Shim is off by default for everything. And there's also the force bind all I was talking about earlier. So we can add a rule. So do add, and then chain will be remote. Use the shim for remote connection. Then policy will be enable. And then we'll do a single port number 8000. So now if we list the rules, you can see that rule is there. So I'll just restart these to get rid of all the TCP. I'll get back in. That one's good already. All right. So now, since we've just enabled the shim for XMMS, if I start playing now, it should use SCTP for the transport. So the one interesting thing to note here, the data is being transferred on this path. And here you can see the heart beatings happening. So SCTP is probing this destination to make sure it's reachable. So by default, the probing is every 30 seconds. That's a thing you can adjust with a syscontrol. So this path is standing by in case there's a failure, which I'll induce by pulling the cable again. And if everything goes correctly, you should start seeing data down here. So it just failed over to this path, and you can see now all the data transfers here, and this one's stalled. So that's the demo.
What happens if you plug it back in?
Will it switch back or will it do it?
So I noticed in the SCTP for 410, it used to stay on the whatever path. So say I unplugged it, it would stay on this path, even if I plugged the first one back in. I noticed now in 7, I guess Randall changed some stuff. It actually, if I plug it in, it should switch back to the original. It'll just take up to 30 seconds for a heartbeat to hit this one before it'll switch. So just switched.
Would you find it quicker if you unplug the other link?
I don't think it matters.
Heartbeat found it.
I can try this one.
No,
So I think the difference is before the demo I had set up. So one of the other things you can see in the sys controls is basically these two, the path RTX max and init RTX max. So what that does is it controls how quickly you fail over from one path to the other. So without, the buffering's not a huge amount that XMMS is doing right now, so it needs to switch over very quickly, like within basically 1 or 2 retransmissions, so you don't have an interruption in playback. And so I think for this side, I didn't change that. So that's one of the things you can tweak. That's why the sys control is actually here. So if you have an application that can tolerate a little bit of loss, then you just leave it as the default, which I think is 4. After 4 retries to the primary destination with no response, it'll switch over. Or in this case, it's set to one time. So you can control how quickly you want based on what kind of application you're using. So any other questions?
When do you expect to be done?
Well,
Sorry.
you'll have to talk to my manager. He's keeping me a little too busy at work these days.
Do you have a plan to patch or?
So when I talked to Randall last, he wanted to get it included when SCTP finally, I don't know what the status of that being in the kernel by default is.
It's in 7.
Okay, so.
But this will not make 7.
Yeah. Oh.
The heartbeat eventually found it. It just had to wait 30 seconds.
Okay. Thank you, Ryan. Thank you. And please accept this as a gift for speaking here.
All right, thank you.
Guys.